In this video, we take a look at sampling quantitative, otherwise known as numerical data. So in StatCrunch, we will open the file M110 NBA Salaries 2019. You can find this file by going to Datasets and then clicking on the search to explore. And I typed in M110 NBA, and it is the second file that comes up from typing in M110 NBA. So we're going to be looking at the NBA salaries from 2019. And we want to take a look at the variables in the data set. So the columns correspond with the variables, and we want to write down each variable name and explain if it's categorical, quantitative, or neither. So the variable rank is just a numbering. We can ignore that, or you could describe it as neither if you like. We have player, team, so those are both categorical data. We have the 2019 to 2020 salary, that's quantitative. We have the salaries for all the other years that are also quantitative. And then if we scroll over, we see we have how the player was signed. And so the ones that are blank, I assume that means the players are still on their contracts. So if they were signed, it explains the category that they were signed with. And then the guaranteed salary, some of these are in scientific notation because they're very large numbers, are quantitative data there. So we can go and note that in part A. So we've got that information noted here. So we are going to begin our investigation with a sampling distribution for the list of salaries. We're looking at quantitative data in this example, so we aren't going to be using the categorical variables. In the quantitative case, a sampling distribution is a probability model that describes the long-run behavior of means or averages from random samples. We can construct a sampling distribution using computer software to imitate taking many random samples to imitate chance behavior. So this process is known as simulation. And we like to use simulation statisticians because we know that it can take a long time to toss a coin many times or roll a die, or in this case, randomly pick values out of a long list of player salaries. So we're going to head into StatCrunch and choose applets and then sampling distributions. And I'm going to arrow back so I'm back here at the beginning in the top corner. You can scroll through and find all your favorite players. So here's my favorite player in row 60, Draymond Green from the Golden State Warriors. So we'll go to applets, sampling distributions. And then we're going to scroll down to the choice to pick our data from a table. And we're going to choose the column to 2019 to 2020 salary. We're going to leave the statistics where it just calculates the mean for us. That's the only statistic we'll be looking at today. Keep it set at use of dynamic seed. A fixed seed would be if we all wanted to see the same random simulation. And then I'm going to give a title to my graph. I'm going to go ahead and call it NBA salaries. And then click compute. So here we see the population distribution graph at the top. So you might notice that this has a big tail out to the right side. That's because there's a few players, such as Steph Curry or LeBron James, with really high contracts making a lot of money. So the second and third graphs are blank. So we are going to do a sample. So our sample is going to be size 2. So I'm going to click one time and we're going to watch our simulation. In this simulation, we picked 2 values at random from the salary distribution. And so that's what we're seeing in the second graph. And then those 2 salary values were averaged and their mean was plotted on the third graph. If I click one time again, I'm going to get a different sample with 2 randomly chosen values in the middle graph. And then their mean is going to be added to the last graph. So let's watch. And in this case, my mean stacked because I got the same mean twice in a row. So let's do this again. And here's my third mean. You can see the arrows down here on the bottom graph, the graph of the means. The red arrow indicates where the median is for these 3 points that I have now. And the green arrow represents where the mean is. And in this case, it's a mean of the sample means. So we're going to keep building up our sample means graph here at the bottom. And the second graph is going to keep changing as we sample two different samples at random. If you're following along on your own computer, you're going to see a similar process, but your samples are going to be different because StatCrunch is sampling at random for all of us. So I'm going to click 5 times and we'll watch the animation. So down here, we've built up a graph of the sample means with many different samples of size 2. If we want to speed up our simulation, we can go ahead and click 1,000 times. And our graph at the bottom shows what the sample means would look like after 1,000 samples, where each sample has 2 different player salaries. So notice our graph at the bottom, we call it the graph of the sampling means, has a right tail similar in shape to the population distribution of salaries up at the top. But notice our graph at the bottom, the right tail doesn't come out quite as far as the population graph. And that's because imagine if you are randomly selecting Steph Curry, the second player that you randomly select is going to be someone with a lower salary in almost every possible chance, right? You'd have to select Steph Curry and LeBron James and average their salaries to get a really high sample mean value, and that's not going to happen very often. So what we see here is a right tail distribution, and then our mean is 7,223,105, and that's pretty close to the population mean salary. And then our median is lower than the mean, what we expect if we've got this right tail, but it's not quite as low as the median salary for the whole population. So now we want to investigate what happens if we take a bigger sample size. So I'm going to adjust the sample size to be 3. That clears off both of my graphs here. And if I do one sample here, I get 3 values chosen, and then we're averaging to find their mean. We'll do another 3 values. We'll watch this a few times and see what happens. So the difference now is that we're pulling 3 values and finding their mean instead of just 2 values. So to speed it up, we can click 1,000 times. And again, we get our graph of the sample means down at the bottom. Now notice this graph of the sample means has a right tail, but it's not nearly as far to the right as the earlier graph. It cuts off before 30 million. Our other graph went a bit higher than 30 million, and our population graph up at the top goes past 40 million. This is because if you're picking salaries at random and one of them is Steph Curry, the other 2 salaries are going to be lower when you're doing your average. So you wouldn't get 3 Steph Currys in a random sample. You would get a Steph Curry and 2 other players with lower salary. And so when you average those 3 players, you're not going to end up with a very high sample mean average. Let's check out what happens if we change our sample size to 5. So if we do our simulation, we're drawing 5 samples at random. We can do another simulation. And so what we're getting down in our sample means graph is the mean of 5 player salaries picked at random. All right, this last sample, we had one high salary up here, close to 40 million in our middle graph from the sample, but notice the other 4 salaries are a lot lower. So the sample mean there was plotted much lower, close to about 7 million. We can speed this up by clicking 1,000 times. And we see here, again, we're getting a right skew graph for our sample means down at the bottom, but the tail is much shorter. And that's because if you pick one player with a high salary, your other 4 players are going to have lower salaries and your average is going to be a lower value. Let's go ahead and check out what happens if we change our sample size to be 10. So if we do one time, we get 10 salaries picked at random. And then our graph of the sample means the bottom plots the mean of the 10 salaries. If we do this 1,000 times, we see our graph is starting to lose that right tail. Because imagine if you pick one of the players with a higher salary, you've got 9 more players to pick at random, and so that's going to lower your average. Your outlying player with the high salary doesn't have as much influence when you're averaging 10 samples as when you were averaging 2 samples. If we go to a sample size of 20, if we hit one time, it just puts all 20 values down for us, and then we could keep clicking one time and building up. the sample means graph down at the bottom. Let's hit 1,000 times the speed of the process, and we see for a sample size of 20, this is starting to look more normal and much less for the right tail. Statisticians like to go up to sample size 30 as the smallest sample size where we start to see a normal shape distribution for the sample means. So you can keep clicking one time and building up your samples of 30 player salaries. You can go straight to 1,000 times and see when our sample size is 30, we start to get a symmetric, normal looking distribution. So we see different screenshots of what we've worked through. And then here we are at question C, where we want to write down a result from the 30 sample size. Now, I wrote this down earlier the last time I did the simulation, so you can see my mean of 7,589,735 is a little bit different than what I just got in StatCrunch, but not too far off, right? The mean that I got in StatCrunch just now with the simulation is 7,580,796. So every random sample is going to give us a different mean, but because we're doing a sample size 30 and we're doing it many times, we don't expect too much variability in our calculations for the mean. Let's see, and you can see the mean and the median are pretty close to each other, and then the standard deviation is around 1,587,000 or so, and this is after 1,000 samples. And if you look back at my draw here, I did 1,017 samples, and my results are somewhat similar. My mean's still a little bit higher than the median, but they're close. And then my standard deviation here is a little bit larger, but still in the general neighborhood of what I got in the previous simulation. So if you're following along in StatCrunch yourself, you should get similar results, but you probably won't get the exact results that I got because it's a random simulation. So we want to explain as the sample size increases, what is the effect on the sample means graph, and to describe the changes that we saw in the graph. So to summarize, as the sample size increases, the sample means graph is closer to a normal distribution. The larger the sample, the less skew in the sample means. And that makes sense because as we're sampling larger samples, we're losing the influence of the outliers. In this case, our outliers were very high salaries from players like Steph Curry and LeBron James. So the next part of this page shows some different screenshots. So these kind of match what we saw when the sample size went from 3 to 5. We lost some of that right tail. When the sample size got to 10, our distribution of sample means down at the bottom started to look closer to normal. And then when we went to sample size 30, it looked much more normal. Question E asks us, would you rather use a small sample or a large sample to estimate the true mean average NBA salary Y? A large sample will be more accurate since outlier salaries like Steph Curry or LeBron James will have less effect on the average if there are n equals 30 samples as opposed to n equals 2 samples. So if our sample size is 30 and you get Steph Curry or LeBron James in your random sample, they're going to get averaged with 29 other player salaries, and so their high salary is less influential. Question F says the standard deviation associated with an estimate is also known as the standard error. So would you expect a point estimate based on a small sample of NBA salaries to have smaller or larger standard error than a point estimate based on a large sample? The point estimate for a small sample, such as n equals 2 or n equals 5, if we're only drawing 2 or 5 salaries, will have a wider sample means distribution graph since outlier salaries like Steph or LeBron have more effect on small samples. So we can say a large sample is going to have a smaller standard error, it's going to be more squished together, and a small sample is going to have a larger standard error. A large standard error means the graph is going to be more spread out. And that's just what we saw if we look back at our screenshots here. When we had the small sample size 3 in the upper left corner, the graph was more spread out. And when we had the larger sample size of 30 player salaries in the bottom right corner, the graph of the sample means down at the bottom is more compressed. We're seeing less variation when we're averaging 30 salaries. Question G asks us to construct a 95% confidence interval for the true mean of the NBA salaries, and then we're going to include a sentence to interpret the meaning. So a confidence interval for quantitative data starts with a sample mean. We say X bar in math symbols, and we're going to add and subtract 2 standard errors because we are working with a 95% confidence level. So this is a similar setup to when we did confidence intervals for proportions. The difference here is instead of starting with the sample proportion, we start with the sample mean. In this case, we're going to use a sample mean and standard error given to us from StatCrunch. So my calculations over here are using the values I recorded on this sheet. So I start at my sample mean of 7,589,735.0177. So that's the sample mean NBA salary. And then we add and subtract 2 times that standard deviation. So I multiplied 2 times the standard deviation first, and then I add and subtract. And so that gave me the lower limit of $4,414,477.97 and an upper limit of $10,764,992.06. So these are the average MBA salary range that I'm trying to predict. So I'm trying to make a prediction for what the real average NBA salary is for all players, and this is the range where I think that real average is in between. So it's not individual player salaries we're trying to estimate here, but the average for all these players. So the way we explain that is with a sentence. And so the way I wrote our sentence here was to say with 95% confidence in our calculations, we predict the mean salary of all NBA players is $4,414,477.97 to $10,764,992.06. So I've got the same structure as in my previous confidence interval sentences, where I've explained that 95% is how confident I am or how sure I am that I've got my calculations correct. And then I'm explaining I'm making a prediction for the mean salary of all NBA players. So that's the mean for the whole population, not just a sample. And then I'm giving the range of values that I think that mean salary lies between. So we could tell someone wanting to know, well, what's the average or mean NBA salary? Well, we're 95% sure it's somewhere between this 4 million and 10 or 11 million. So now we want to use StatCrunch to find the mean and standard deviation of the whole population because we have all the data here. If we're doing estimates in real life, we don't often have the whole population data, so we just estimate with samples. So I'm going to go into StatCrunch and select Stat, Summary Stats and Columns in my same data set here. You can close out your sampling distribution by hitting X if you want to come back to it. Just click on StatCrunch Results and you can bring it back up. So we'll go Stat, Summary Stats Columns, and we're looking at the 1920 salary, and we want the mean, and we want the standard deviation. You could also click the median if you want. So I'm going to hold down Control or Command and click standard deviation as well. And so here's the mean and standard deviation for all of the MBA salaries in our whole data file. So I recorded those values here. So the mean is $7,536,755.40. And then the standard deviation is $8,865,552.80. So that's a really big standard deviation because we're looking at the population graph. So if you go back to our results, this top graph is a population graph up here. And in the population graph, those salaries are really far spread out because we have the outliers with the real high salaries, Steph and LeBron. So you can see the standard deviation for the whole population is really, really large, whereas the standard deviation for the graph of the averages down at the bottom, the sampling means graph, is much more compact or put together because that's just a graph of the means, and so we don't have the outlier salaries in there. So now I'm going to ask you to take your standard deviation and divide it by the square root of 30. We're using 30 because that's how many samples we had. We had sample size 30 in our calculation And so we take the $8,865,552.80 and divide that by the square root of 30, which rounded is about 5.4772. And so that gives us a value of 1,618,628.64. So if you look back in our sampling distribution, that's really close to the standard deviation we have down here for our sample means. So you can imagine if we take a bigger sample, our graph of the sample means is going to get more squished together. So we need some sort of way of estimating what that standard deviation is going to be for the graph of the sample means. And so we have found mathematically that if we take the standard deviation for the whole population and divide it by the square root of the sample size, that gives us a sense of how squished or compressed the sample means graph is. So we note here that this value is very close to the sampling distribution standard deviation that we recorded back in part C. So these are some important results that we've observed. So the first big result is that the standard deviation of the sampling distribution is smaller than the population standard deviation. In general, when a population has a mean mu and a standard deviation of sigma, the distribution of all possible sample means from this population will still have the same mean. So if we look back, our mean, the arrows down here haven't changed too much. The mean here was 7,580,000 and change, and the mean for the whole population was 7,536,000 and some change. So the mean doesn't change too much, so we say we're still going to expect the same mean. But we know the standard error shrinks, so we say the standard error shrinks by a factor of sigma divided by square root of n, where n is our sample size. So notice when we did the simulation, our standard error value is noted as a standard deviation. So what we think of as a standard error is also sometimes called the standard deviation for the sample means graph. So you could either describe it as a standard deviation for the sample means or use this term standard error, your choice. And then we put a note here, n has to be a number of independent observations. So since we're drawing at random in our simulation, each observation is independent. If you had a room full of people who were related in some way or a bunch of students all from the same class, our observations wouldn't be independent. If a sample consists of at least 30 independent observations and the data are not strongly skewed, then the distribution of the sample means is well approximated by a normal model. So when we did our sample size 30 here in our simulation, our graph of the sample means down at the bottom looks pretty close to normal. So our general rule of thumb is if your sample size is 30 or more, then you can assume the sample means graph will be close to a normal shape or a normal model. And then our third important idea is that a reliable method to ensure sample observations are independent is to conduct a simple random sample consisting of less than 10% of the population. So this is a general rule of thumb. If you take a sample that's more than 10% of the population, you might end up getting people who are related in your sample, or your sample might be too big to give realistic results. So these results are known as the Central Limit Theorem, or for short we call it the CLT. So our Open Intro to Statistics text over on page 172 to 177 has an in-depth explanation. These three key points are the big ideas of the Central Limit Theorem. And then there's a note here. It says, but wait, there's one issue with the equation sigma divided by square root of n. The population standard deviation, that's sigma, is typically unknown. How do we resolve this problem? So we can use a point estimate of the standard deviation from the sample, and we calculate s divided by square root of n, where s is the sample standard deviation. So this estimate tends to be sufficiently good when the sample size is at least 30 and the population distribution is not strongly skewed. So we are going to be using these calculations to make confidence intervals to predict averages for populations. So we'll take a look at that in some of the next examples.